Hello guys, welcome to this bunch of tutorials in which our major aim is to understand numerically, mathematically how does we formulate things, how does we solve problems. Okay. Now most of the contents that we will be looking in these bunch of tutorials now are considered to be prerequisites. So you can think of these as a small recap of whatever ideas that have been discussed in the first level course of machine learning. So what are the topics that we shall be covering? Now we expect from the viewers of these tutorials that they are comfortable with the idea of maximum likelihood estimation, with EM algorithm, backpropagation numerically, so not having an intuitive view of how does it happen in a system using dot backward, loss dot backward, that is not what we expect. We expect that the students or the viewers of these tutorials have been equipped with necessary mathematical foundations to understand these things. Okay. So without any further delay, so now let us jump in. In the first numerical problem, our main aim is to understand maximum likelihood estimation, MLE estimation. So now the problem goes like this: let I have this x which is from a normal distribution with mean mu and variance 1. Now from this distribution, now we have n IID realizations. We have n IID realizations of x. Okay. But what we have done is, while taking the observation, okay, we did not take down the actual value of the observation, we only noted whether it is positive or not. Okay. So while taking down the observations, we only noted whether or not value is positive. Okay. Now suppose m of n observations that we have recorded have negative values, find the maximum likelihood estimation of the parameter mu based on these observations. Okay. I am assuming that the problem setting is pretty much clear. I am having n IID realizations from this distribution which is there, and this distribution has only one parameter mu, and now from the writing it should be clear that these are scalar valued random variables which we are dealing with. Okay. So now while going ahead with that, we only noted whether it is positive or not. Now out of these n realizations that we have, now m of them is negative. Now what is the maximum likelihood estimation of this mu which is there? Now how do we go ahead and calculate this? So now let us go into the solution. Okay. Now we know that the probability of x taking the value less than 0 is probability x minus mu divided by 1 less than 0 minus mu divided by 1. Okay. Here standard deviation is 1. Now this is we are standardize x standardize x. Now this will lead to, this is probability of z less than minus mu. Now here since we have standardized, z is from the distribution 0 1, okay, and we know this value from the properties of normal distribution. We know this value, this is phi of minus mu, okay. So now similarly, now the probability of x greater than 0 is 1 minus probability of x less than 0, this is 1 minus phi of minus mu, this is phi of mu. Now here, now at these points we are using this is using normal CDF inverse. See, I am assuming that these ideas which are there are clear and comfortable, okay. So this directly means that you would have undergone a rigorous course in probability theory and then a rigorous course at a first level machine learning, okay. So now coming to the data, now we have m, now which is number of negative observations, okay. So and then n minus m is number of positive observations, okay. Now for each of the observation which we can immediately say that observation, take what is the probability of it being positive or being negative. For each observation, so probability that it is positive is phi of mu, probability that this is negative is phi of minus mu. Now with this, how can we go ahead and find the likelihood of the observed data, okay. So now likelihood of observed data that I represent with L of mu is probability that x takes value less than 0, have m of them, and probability that x takes value greater than 0, I have n minus m of them, okay. Now this is phi of minus mu to the power of m into phi of mu to the power of n minus m, okay. So now this is the likelihood. Now what do? We normally take the log, okay. So now taking the log, that we represent by L of mu is log of capital L of mu. Now this is log of phi of minus mu to the power of m into phi of mu to the power of n minus m. So now by using the log properties, now we can immediately see this as m log phi of minus mu plus n minus m log of phi of mu. Now just for the sake of simplicity, now we prefer to go ahead with some kind of substitution. So now we can simplify by substituting let us say that P is probability that x is less than 0, this is phi of minus mu, and 1 minus P is probability x greater than 0, this is phi of mu. Now we can easily substitute these. Now because of which, how does now the likelihood term looks like? So now the likelihood becomes I am saying likelihood, not log likelihood. Now it becomes L of P to the power of m 1 minus P to the power of n minus m. Okay, this is what it becomes. Okay, does this ring a bell? Does this formulation ring a bell? This is exactly the likelihood of Bernoulli. Okay, so wherein which I am considering the negative term is treated as success. So you have m success that has been observed in n trials. Okay, so now this is exactly the likelihood of Bernoulli model, where the negative is treated as success okay, and then we have m success that has been observed out of n observations or n trials. So n success are observed in n trials. Now what do we do? First we find the MLE for P and then we convert back to mu, that is the standard idea. Now let us take the log likelihood. L of P is m log P plus n minus m log of 1 minus P. Now how do we go ahead with that? We differentiate with respect to P and then equate it to 0, the standard idea. Okay, we want to get the maximum likelihood, so you get the log likelihood, so and then differentiate it with respect to whatever the parameter that we are looking for, so and then equate it to 0 and then simplify it. So now differentiate with respect to P and equating to 0, d by dP of this L of P is m by P minus n minus m divided by 1 minus P. So this is the thing. Now you equate it to 0. Now equating to 0, this is m by P minus n minus m divided by 1 minus P is equal to 0. Now it will be m into 1 minus P equals n minus m into P. Now this will straightforward say that P is equal to m by n, which implies the MLE thing for this P hat, that is how we represent. Now this is m by n. Okay. Now this is something that is straightforward known to us. The MLE is the probability of getting a negative observation. So you have got m negative observations, so out of them n. Okay. Now this P hat which is there, now we have to convert P hat back to mu hat. Now what is this P? The value of this P is phi of minus mu. Okay, that is how we started. Now we have to represent them in P hat terms. P hat is mu of minus mu hat. Now this is m by n is phi of minus mu hat. Okay. So now we know that if phi of A equals to B implies A is equal to phi inverse of B. Now in this case A is equal to minus mu hat, B is equal to m by n. So if we substitute this, so we get minus mu hat is phi inverse of m by n. Okay. Now which is mu hat is minus phi inverse of m by n. Okay. So now we know that minus phi inverse of q, if we have, this is same as phi inverse of 1 minus q. These are the standard properties of the standard normal which is there. Okay. And then it should be very much clear that we are dealing with standard normal. Now we have this mu hat is phi inverse of 1 minus m by n. Now this is therefore this mu hat is equal to phi inverse of n minus m by, this is the MLE estimate that we have obtained for this mu hat. Now this is intuitively clear for us. Okay. Now if we go back to this term which is there. Okay. So now if we have many negative observations, so what does that mean? If we have many negative observations, so then what will happen is m over n, which is there, will be large enough. So therefore this term phi of minus mu hat now will be large. Okay. This means that this mu hat minus mu hat which is there now is positive. So that means that the estimated value, the estimated maximum likelihood estimate that we have obtained for this particular mu hat is negative. Now this makes total sense even for us. If many observations are negative, so then it is a straightforward indication that the normal distribution should have a negative mean. Now that is what now we are trying to look at this point. Okay. Now this is how we go ahead. The standard method is, know which parameter you want to go ahead, find the likelihood, find the, and then get the log likelihood, differentiate with respect to 0 and equate it to 0. This is the standard method of using MLE estimate. Okay. I assume that this is clear. So in addition to that, I just want you to bring it to the notice that you should be very much comfortable with another estimation which is map estimation. So I will leave it to the viewers to have a recap of that as well. Okay. So now in the next problem that we shall be dealing with, now let us go into one of the very interesting ideas which is EM algorithm. Okay, expectation maximization algorithm. So now let us look into it. Now it will give you a nice recap of how the EM algorithm works and then how to solve and get the closed form solutions for the parameters. Okay. So now the density of x is a mixture of two exponential densities. Okay. Two exponential densities. Okay. So now then for any given observation x which is parameterized by theta, now how does this look like? You have this pi beta 1 e to the power of minus beta 1 x plus 1 minus pi beta 2 e to the power of minus beta 2 x. Now here what are the parameters, what are this theta represents? So theta is pi beta 1 beta 2. Okay. Now this pi is the probability of choosing from the component 1, the first exponential density, and 1 minus pi is the probability that you are choosing from the second exponential density which is there. Now therefore this pi has to be between 0 and 1, and this beta 1 and beta 2 has to be greater than 0. So this pi which is there is between 0 and 1, and this beta 1 is greater than 0 and beta 2 is also greater than 0 as per the exponential densities. Okay. Yeah, we can use equal to here, that is fine. Okay. So now what are we supposed to do on this? So we are supposed to use EM algorithm. So use expectation maximization algorithm. So now how we should do it? Now use a scalar binary z, okay, as a latent variable. So now you can think of it like this: I have a coin, I will just toss it. If it is head, I will choose from component 1, if it is tail, I choose from component 2. So equivalent of saying that. So and show the E step, Q function and M step. So that means that just go through the whole EM algorithm once is what is being said here. Okay. So now let us go into the solution. So I assume that the question is clear. So now you have a mixture of two exponential densities. So now you have to go ahead and obtain the forms for these parameters which are there. Okay. So now let us go ahead with that. Okay. So now let us look into the solution. Z is there, takes the value 1 if x comes from component 1, it takes the value 0 if x comes from component 2. Okay. This is what we have. So this is a straightforward indication that Z is a Bernoulli with pi. Okay. So now we have this f of x parameterized by theta. Okay. Oh sorry, f z x z. So we want the complete data. Okay. Now what do we have is x1 x2 so on till xn observations. Okay. So now for each xi, there is a hidden latent variable zi. There is a hidden variable zi which is there. Okay. Now therefore how does the complete data look like? Now therefore the complete data is x1 z1 x2 z2 so on till xn zn. Okay, this is what we have. So now all these observations are IIDs. Now therefore the joint complete data distribution data density is represented by this f of x z parameterized by theta is the product of I is equal to 1 to n f of xi zi parameterized by this theta which is there. Now this we can substitute. We know this is I is equal to 1 to n. Now how it will be, this we can write as pi b1 e to the power of beta 1 x I to the power of zi into 1 minus pi beta 2 e to the power of minus beta 2 xi to the power of 1 minus zi. See, it is quite simple. See, what are the values that each zi can take? Now each zi can take 0 or 1. Now let us say that zi is 1, okay. Now then this will be 1, okay, because of which it is coming from component 1. Now therefore 1 minus zi, it will be 0. Now therefore this whole thing will be 1, okay, this will become 1. So therefore you will only be considering this, okay. Now if zi is 0, that means that it is coming from component 2. Now then this will be 0, because of which this whole thing will be 1. Now this is 1 minus 0 is 1, so therefore you will be choosing from this, okay. So this makes sense, I guess. Now then what you are supposed to do, now this is the complete data density. Now you take the log, okay. Now taking log, L of theta is log of z parameterized by theta. Now this is a product. So now you can immediately apply the rules of logarithms, and then now this will become summation I is equal to 1 to n log of pi beta 1 e to the power of minus beta 1 xi raised to the power of zi plus log of 1 minus pi into beta 2 e to the power of minus beta 2 xi. So this is what so the log term will become. Now we can further simplify this by taking the log inside. So now this will be summation I is equal to 1 to n, this will be zi log pi plus log beta 1 minus beta 1 xi plus 1 minus zi into log of 1 minus pi plus log of beta 2 minus beta 2 xi, okay. I am using the rules of logarithms, I assuming that these things are clear, okay. So now what is that? Now we are using EM algorithm, we do not know what is this zi. Now in each step what is that we are supposed to do? In each step we compute the expected value of zi. So now let us start doing it. So now in each step, so we compute expected value of zi for a given xi, okay. So given observed data and current parameter estimate. See, just for the sake of clarity I use another thing what is known as theta old, just to indicate that the old parameters and the updated parameter. Updated parameters I leave it as theta. Okay. So now this is pi old, beta 1 old and beta 2 old. Okay. So I know that the equations will become more cluttered, but I am assuming that all of you are capable enough to take care of these things. Okay. So now what is this mixing coefficient which is there? This is expected value of Zi given Xi parameterized by theta old. Now how does this will be? Now do we know this expected value? Yes. Now this will be probability of Zi equals to 1 given Xi parameterized by theta old. And can we compute this value? Yes, apparently we can compute this value going ahead with the Bayes rule. This is f of Xi given Zi is equal to 1 parameterized by theta old into probability of Zi taking the value 1 parameterized by theta old divided by f of Xi parameterized by theta old. This is from Bayes rule. Okay. I assume that those basic ideas are crystal clear. So now what value it will take? Now this is pi old. What is this pi old? Is because of this. Okay, taking the value 1 and now given it is from the component 1. Now it has to be beta 1 will be the parameter. Now this is beta 1 old into e to the power of minus beta 1 old Xi. This is the numerator term. This is for this, okay, and this pi old is because of this. Okay, fine. Then this divided by, in the denominator I will have a pretty big term. This is pi old beta 1 old e to the power of minus beta 1 old Xi plus 1 minus pi old beta 2 old e to the power of minus beta 2 old into Xi. Okay, fine. Now this is the probability that for a given Xi, now Zi is taking the value 1. Now similarly we have probability that Zi taking the value 0 given Xi parameterized by theta old is 1 minus the coefficient. Okay, and this is same as the expectation of 1 minus Zi given Xi parameterized by theta old, which is 1 minus the coefficient. Okay. Now this completes the E step. We have computed this expectation now which is there. Now let us go into the Q function now which is there. Okay. This completes the E step. Now the Q function. Now the Q function, see in couple of treatments they do not use this Q function, they do not name it and then they just go ahead with that. Maybe people whose treatment was not using this term Q function, this is not a standard term which is there, but it is an intermediary step that comes in. Okay, this is Q of theta given theta old. This is expectation of Z given X parameterized by theta old of the log of theta. Okay, and this, now this is expectation of z given x parameterized by theta old, this is log of f of x comma z theta given x parameterized by theta old. Now we know this already, we know the inner term. Okay. Now this is, there is an expectation, the log term we already know, this is a summation I is equal to 1 to n zi into log pi plus log of beta 1 minus beta 1 xi plus 1 minus ci log of 1 minus pi plus log of beta 2 minus beta 2 xi. Okay. And this is using the rules of expectation. So expectation of summations, you can take the expectation inside each one of them. So what I will do is I will term this whole thing as ai and I will term this whole thing as bi. Okay. So now then what happens is, now we can take that expectation inside. So expectation of zi ai, the expectation with respect to z given x. So this will be expectation of zi into ai. Now we already know this value. Now this is into ai. Now similarly expectation of 1 minus zi into bi, this is expectation of 1 minus zi into bi. We already know this also, this is 1 minus of the coefficient into bi. Okay. Now using these, you take all those expectations inside. Okay. Now you take this expectation which is there inside of this expectation of, for each term of this whole thing, this is zi into ai. So it will be coefficient into ai, this is 1 minus of the coefficient into bi is what you will get. Okay. So now therefore the whole term will be, this whole summation I is equal to 1 to n coefficient into ai, which is log of pi plus log of beta 1 minus beta 1 xi plus to this into log of 1 minus pi plus log of beta 2 minus beta 2 xi. You get this. Okay. So now next what? Now you want to maximize this. Expectation step is done. Now this is the outcome of the Q function. Okay. Now this is what is known as a Q function. People may know it without that name as well. That's perfectly fine. So now what is the next thing that is supposed to do? Now this which is there, this term which is there, now you have to go ahead and differentiate with respect to each of the parameters. You have 3 parameters, pi, beta 1 and beta 2. You have to differentiate with each of those parameters and then equate it to 0 to get the values. Okay. So now whenever you are going ahead and differentiating, now with respect to, let us say that you take the pi term, so only this will come. Okay. Only this term will come. You take and multiply inside, only these 2 terms will come. Okay. Now if you go ahead with beta 1, so you get this multiplied by this. and this, yeah, and this, sorry, and this. So these terms now will come. So whenever you are differentiating with respect to this whole thing, since it is independent of beta 1, so this you will not be taking ahead, and similarly with respect to beta 2. So now what I will do is I will just simplify this for each of the term. Okay. So now let's do the m step. Okay. Now let us do this m step now which is there. Now what is the first thing, this q function which is there with respect to pi. Now how does it look like? Now this is summation I is equal to 1 to n, you have this coefficient log of pi plus 1 minus of this into log of 1 minus pi. This is what you have. Now then you have to take this and take the partial derivative with respect to pi of this q pi. Now this will be summation I is equal to 1 to n minus 1 minus the coefficient divided by minus of this, and then you equate it to 0. So equating this to 0, now you get equating to 0, you will get 1 minus pi summation is equal to 1 to n, the coefficient is 1 divided by 1 minus pi, this is summation I is equal to 1 to n 1 minus this. So now let us substitute something, s is summation I is equal to 1 to n pi. Now this immediately goes that the summation I is equal to 1 to n 1 minus of this will be n minus s. Okay. Now if you substitute this will be s by pi equals n minus s by 1 minus pi. Okay. Now therefore if you solve this, so now for the new value you get 1 over n summation I is equal to 1 to n, this coefficient is what you get. Okay. Now this is for the pi value. Now let us look at for beta 1. Now m step for beta 1. So similarly I write this q function with respect to beta 1. So it will be summation, only the first term will come into picture here, coefficient into log of beta 1 minus beta 1 xi. Okay. Now then what you are supposed to differentiate with respect to beta 1 and equate to 0. Okay, standard terms. Now differentiate with respect to beta 1 and equate to 0, and what do you get? Summation I is equal to 1 to n into 1 over beta 1 minus xi equal to 0. Now this will be 1 over beta 1 summation I is equal to 1 to n summation I is equal to 1 to n this. Okay. Now therefore now beta 1 nu will be I is equal to 1 to n divided by okay. Now this is how beta 1 nu will look like, and similarly you perform a similar thing. Similarly for beta 2 you get beta 2 nu is summation I is equal to 1 to n 1 minus of this summation I is equal to 1 to n 1 minus of this into xi. Okay. This completes the whole thing. Okay. Now this you go ahead in what do you call in loop, and then you solve for the parameters. Now EM in an iterative fashion you go ahead and do it. Okay. Now this section of tutorial we will stop at this point. So in which we just saw now how can you go ahead and solve in terms of MLE and in terms of expectation maximization. See, the overall aim of this is to reiterate or re-emphasize the ideas that you might have to an extent what do you call sunken inside. So just to bring it to the surface so that we will be needing these ideas as we go ahead with respect to the generative models. Okay, that is the sole purpose of this. Now this section of tutorials is we end at this point. In the next section of tutorials we will be working on couple of neural network based numerical problems. I hope this section was not too heavy and then you are comfortable with solving the idea. The standard idea is this, you get the likelihood, differentiate with respect to whatever parameter that you have and then equate it to 0. Okay, this is the standard thing that we have used. I hope that is perfectly clear, and then you are very much comfortable with using these what do you call these tricks of the trades. Okay. Now that is you will be able to understand the mixture densities, you will be able to understand how do you go ahead with the standard differentiation and other things, the standard ideas which are there. Okay. Now with this we conclude today's discussion. So thank you all for going through this session. Now we will be meeting again with respect to couple of numerical problems on neural networks in our next section of tutorials. Till then, bye bye, have a nice day. Thank you.